Summary measures provide precise, objectively determined values that are easy to calculate, interpret, and compare with another. We have 4 types of summary measures. The first one is central location. It measures a typical or central value in the data. The second one is dispersion. It measures the variability in the data. The third one is shape. They measure whether or not the distribution is symmetric. And the final one is association, and they measure whether two numerical variables have a linear relationship. Let's start with the first one, central location. The term central location refers to how numerical data tend to cluster around some middle or central value. Measures of central location attempt to find a typical or central value that describes the data. The arithmetic mean is the primary measure of central location, and it can be referred to as the mean or the average. So we find mean as follows. Let's say our data is 1, 1, 2, and 4. So the mean or the average of this data is you sum all observations and divide by number of observations. We have 1, 2, 3, 4. So divide by 4. So this is 8 divided by 4. 2 is the mean. The only thing that differs between a population mean and a sample mean is the notation. So for population mean, we use the notation mu, and for sample mean, we use the notation x bar. The mean is used extensively in data analysis. However, it can give a misleading description of the center in the presence of extremely small or large observations or outliers. Now let's see this example. Let's say our data set is 1, 1, 2, 4, and then 92. So as you see, 92 represents the outlier or the extreme value. So let's find out the mean for this data set. 1 plus 1 plus 2 plus 4 plus 92 divided by, this time we have 5 observations. So that is 100 divided by 5, 25. So as you see, the mean is between the fourth and the fifth variable. So this doesn't show the center of the data set. Therefore, mean is not a good measure if you have an outlier or extreme values in your data set. So for that reason, we calculate the median as a measure of central location. Median is the middle value of a data set. So that means when you find the median, let's say this is the median, you have equal number of observations below the median, and you have equal number of observations above the median. So let's find out the median of the last data set we have. The middle is 2. So one thing you need to know, if you have odd number of observation, then the median is in the middle. If you have even number of observation, like in this case, the median is the average of two middle values. The median in this case is 1 plus 2 divided by 2, which is 1.5. If the mean and the median are different in your data set, it's likely the variable contains outliers. And the last central location measure is mode. The mode of a variable is the observation that occurs most frequently. So if you take this data set 1, 1, 2, 4, the mode is 1 because 1 occurs most frequently. The function for mean is average. So we type equal sign and then average, and then open the parentheses and select the data. And then close the parentheses. So the mean or the average value for growth mutual fund is 15.11%. And you can just drag formula and you can see that the mean value for the value fund is 11.44%. For median, we have a median function. Now you are going to select the data for the growth funds, and you can just copy this formula here. So the median is 14.44 for the growth, and for value it's 15.09%. Next, we talk about dispersion. Measures of central location do not describe the underlying dispersion. Measures of dispersion gauge the variability. So if you have 0 for measures of dispersion, that indicates all the observations are identical. And dispersion increases as the observations become more diverse. We start with the range. Range measures the difference between the maximum and the minimum. So let's go back to our data set 1, 1, 2, 4. So the maximum number is 4, minimum number is 1. So the range is 4 minus 1, 3. The interquartile range, or IQR, measures the difference between the third quartile and the first quartile. So in this data set, first quartile is 1, the third quartile is 2, IQR is 2 minus 1, 1. Mean absolute difference, or MAD, is the average of the absolute differences between the observations and the mean. If you remember, the mean for this data set is 2. And now we are going to calculate absolute differences, which in this case 1 minus 2. I take the first observation and subtract the mean and take this number into absolute function. So the result is minus 1 in absolute function, and that's equal to 1. 1 minus 2, 1, 2 minus 2, 0, and 4 minus 2, 2. So we sum all of them and divide by the number of observations. Mean absolute difference for this small sample is 1. The variance and the standard deviation are the most widely used measures of dispersion. For calculating variance, we first need differences. So the differences are minus 1, 0, and 2. So how we find this? 1 minus 2, okay? And then you square these differences and then sum them up, which will be 1 plus 1 plus 0 plus 4, and divide by the number of observations if you calculate the population variance. So population variance, you divide by the number of observations. Then you divide by 4. If it's a sample variance, you divide this sum by n minus 1, which in this case 4 minus 1, 3. Standard deviation is the square root of variance. And finally, one last important measure that I'm going to talk in this video is Sharpe ratio. Sharpe ratio is reward to variability ratio. The Sharpe ratio is often calculated as xi bar minus rf divided by si, where xi bar is the mean return for investment I, rf is the mean return for a risk-free asset such as treasury bill, and SI is the standard deviation for investment I. The numerator of the Sharpe ratio measures the extra reward that investors receive for the added risk taken. This difference is often called excess return. The higher the Sharpe ratio, the better the investment compensates its investors for risk. Next, I'm going to show how you can calculate range, variance, standard deviation, and Sharpe ratio using Excel. To calculate range, we need to find maximum and minimum value for growth and value mutual funds. Maximum is the max function in Excel, and you select the returns for growth and close the parentheses. And to calculate for value, you can just copy this formula here. Minimum is min function, and the same we can copy this formula here. Range is the difference between max and minimum. Again, we can copy this formula for value. Variance, we will use variance function for sample. So that's why we are choosing var.s and we select the data. Close the parentheses and we copy this formula for value funds. Standard deviation function, and we select the data. We copy this formula. Mean, we use average. Let's assume that the risk-free rate is 2% and the Sharpe ratio is calculated as the difference between mean return and the risk-free rate divided by standard deviation. The third category of summary measures measures the shape of a distribution. A symmetric distribution is the one that's a mirror image of itself on both sides of its center. The skewness coefficient measures the degree to which a distribution is not symmetric about its mean. A symmetric distribution has a skewness coefficient of 0. For that reason, the normal distribution has a skewness coefficient of 0. A positively skewed distribution has a positive skewness coefficient, whereas a negatively skewed distribution has a negative skewness coefficient. If two return distributions are the same except for skewness, for example, they have the same mean and standard deviation, investors would prefer the distribution with positive skewness because that distribution implies a greater probability of extremely large gains. The kurtosis coefficient is a summary measure that tells us whether the tails of the distribution are more or less extreme than the normal distribution. A distribution that has tails that are more extreme than the normal distribution is leptokurtic. A return distribution is often leptokurtic, which means that its tails are longer than the normal distribution, implying the existence of outliers. If a return distribution is in fact leptokurtic, but we assume that it's normally distributed in statistical models, then we will underestimate the likelihood of very bad or very good returns. A platykurtic distribution is one that has shorter tails or tails that are less extreme than the normal distribution. Excel calculates excess kurtosis. The excess kurtosis is the kurtosis coefficient minus 3. A positive coefficient represents more extreme tails than normal distribution. A negative coefficient represents less extreme tail than a normal distribution. In Excel, there is skew function to calculate skewness. In Excel, there is kurt function to calculate kurtosis. Let's summarize our findings. Skewness of the returns from the growth mutual fund is very close to zero. That indicates the distribution is symmetric. For value fund returns, the distribution is negatively skewed. Excess kurtosis for both returns are positive. That indicates the distribution is leptokurtic and there are outliers in the distribution. A positive excess kurtosis also indicates that there are more extreme tails than a normal distribution. The fourth category of summary measures are measures of association. In the previous videos, we use a scatter plot to visually assess whether two numerical variables had some type of systematic relationship. Here, I represent two numerical measures of association that quantify the direction and strength of the linear relationship between two variables x and y. It's important to point out that these measures are not appropriate when the underlying relationship between the variables is nonlinear. We start first with covariance. Covariance measures the direction of the linear shift between two variables x and y. If the covariance is negative, then x and y have a negative linear relationship. If the covariance is positive, then x and y have a positive linear relationship. If the covariance is zero, then x and y have no linear relationship. The covariance is difficult to interpret because it's sensitive to the units of measurement. That means the covariance between two variables might be 100 and the covariance between two other variables might be 100,000, yet all we conclude is that both sets of variables have a positive linear relationship. We cannot comment on the strength of the relationship. On the other hand, correlation coefficient describes both the direction and the strength of the linear relationship between x and y. The correlation coefficient falls between -1 and 1. If the correlation coefficient equals -1, then x and y have a perfect negative linear relationship. If the correlation coefficient equals 0, then x and y are not linearly related. And a correlation coefficient of 1 indicates a perfect positive linear relationship between x and y. Other values for correlation coefficient must be interpreted with reference to -1, 0, or 1. For instance, a correlation coefficient equal to -0.8 indicates a strong negative relationship, whereas a correlation coefficient equal to 0.12 indicates a weak positive relationship. To calculate covariance, we have a covariance function in Excel. We choose covariance S for the sample. The first variable x is growth. The second variable is value. For correlation, we have correl function. And again, our first array is growth. Second array is value. The correlation coefficient between growth and value of 0.6570 indicates that the variables have a moderate positive linear relationship. In other words, on average, when one fund's return is above its mean, the other fund's return tends to be above its mean and vice versa. In order to diversify risk, an investor is often advised to invest in assets such as stocks, bonds, and mutual funds whose returns are not strongly correlated. If asset returns do not have strong positive correlation, then if one investment does poorly, the other may still do well.